Hey class, today's lesson is lesson number 10, looking at the tissue level of mechanics of the human frame. Here's the learning objectives from the book, but we're looking at the material mechanics, so this section is going to focus on the internal effects of forces and moments. So we're looking at tissue mechanics, we're looking at bones, ligaments, cartilage, and tendons. So basically, there's just mechanics of materials of human connective tissue. So first we're going to start with a load. So what is a load? It's an externally applied force. Okay, and how an object responds to a load is going to be determined by the magnitude of that force, location, direction, duration, frequency, variability, and the rate of loading. So the types of loading that we have axial, bending, as well as shear. Axial, we'll look at compression, tension, bending. We have 3-point, 4-point. Bending, and then shear we have direct and torsion, which you might have heard in previous classes. So with axial loading we have compression, which is a load that squeezes parts together. Tension is a load that pulls things apart. Bending is a load applied perpendicular to the longitudinal axis of a body, which causes it to curve. Okay, for 3-point bending typically creates 2 moments, and for 4-point bending we have 4 forces that are applied, and 3-point we have the 3 points that are applied. For shear loading, it's a load that causes one part of the body to move parallel past another, so think of it as cutting paper is a good example of that. And then torsion is more of a twisting around an axis. Think of torsion when you try to open up a water bottle or Coke can. Not Coke can, but Coke bottle. So the difference between mechanical and material properties. So material properties tell you the material that makes up the body, how it responds. So tell you how the material that makes up the body responds to loading. So material properties use mechanical properties to tell us a little bit more about the structure. And then mechanical properties tell you how a body as a whole responds to a load. So mechanical properties are determined by the material properties, and when we're looking at mechanical properties, we're looking at strength, deformation, stiffness, as well as toughness, and we'll define all of those here later on. With strength being the amount of loading that an object can withstand before failure, again relating this to your human body tissue. Deformation, okay, so is a change in the dimensions of a body. So we have those axial loads that are determined as a change in length. Something can be brittle, which is characterized of an object that can undergo very small deformation, something like glass. Ductile, something can be ductile, in which it characterizes an object that can undergo very large deformations, such as gum. Then we have elastic and plastic deformations. So elastic deformations is deformation in which the object returns to its original dimensions, like a rubber band. Plastic is you've gone far beyond its elastic component and it's not going to return to its original shape. Okay, that would be the plastic that holds a 6-pack of soda together, right? So that plastic, once you stretch it out, it does not come back together. And then there's this yield point in between an elastic and plastic region. So it's the amount of deformation that marks the transition from elastic to plastic. So deformation beyond this point results in the permanent plastic deformation, or we could also think of it as micro-tearing. So to look at how an object responds to a load, so the deformation in response to a load, we can look at stiffness and compliance. So if we think of something in which there is a lot of deformation and a little load, it's going to be less stiff. Meaning a lot of deformation and a little load would make something more compliant. So stiffness being the ratio of the change in load to the change in deformation, and compliance the ratio of change in the deformation to the change in load. So just kind of different perspectives of looking at those. Toughness is the amount of energy that can be absorbed by a body before failure. And we talked about this last class on strain potential energy. Okay, strain is potential energy because of the possibility that the energy absorbed by the body can then be reused. Just like when we land and then go to jump, Okay, our tendons develop strain potential energy. So it's the amount of energy that can be absorbed by the body as a result of deformation. Think of our tendons, okay, absorbing that energy. So we can look at this load deformation curve. We see stiffness, which is the slope of the force deformation curve. Okay, stiff is not necessarily stronger, however it can be. You can be stiff and strong, stiff and weak, can be strong and compliant, or strong and weak. Or you can be also, not strong and weak. Okay, you can be strong and compliant, or you can be weak and compliant. Then the area under the curve is the energy absorbed by the material. So it's the toughness or the strain energy. Something that is weak and compliant can technically absorb something that is as much strong as and stiff. So here you see this elastic region, you see the yield point, and then our plastic region, and then the energy, and then obviously the stiffness. If we're looking at force deformation, load deformation, okay, is going to determine whether the slope of this says how stiff it is. So looking at the compare contrast of the mechanical and material properties. So again, material properties use mechanical properties to tell us more about a structure, where mechanical properties are determined by the material properties. Okay, so we have mechanical property, material property, force, we have stress, we have deformation, we have strain, stiffness, then we have the Young's modulus, elastic modulus, we have strain energy, then we have strain energy density. We're going to talk about some of these material properties a little bit more. So stress is the way a force is distributed within a body. Okay, so we see force over a given area. A bigger area or a smaller force, then it's going to decrease the amount of stress. So if you think about it, a good example is someone who lays on a bed of nails, right? Okay, we've seen that before, maybe in movies. Okay, as the number of nails, though, decrease, right, so the area, okay, the force per nail will increase, okay, meaning there will be more stress in that general area, which can then cause, obviously, a puncture wound. Then we have strain is the change in dimension normalized to the original dimension. So strain tells us how far something was stretched, for example, based on its original length. So a change in length relative to the original length. Then we have the elastic modulus, which is the slope of the stress-strain curve. Okay, so we're talking about material properties. So how elastic something is. A low Young's modulus is something that is very compliant. So we are looking at stress and strain. Strain energy density is going to be relative to the amount of energy stored by the material. So if we look at the stress-strain curve, looks very similar, okay, to our load deformation curve, right? So we have the Young's modulus or elastic modulus right here. We have our strain energy as the area under the curve, okay, and then elastic plastic regions and our yield point, okay? So our question as we move on is, Cindy is a client of yours who needs to increase her flexibility, so we're going to start talking about some principles of muscle with flexibility. How can you use your knowledge of viscoelastic materials to instruct her on proper stretching techniques? So what we end up seeing is that the longer you hold a stretch, there's a decrease in stress when the strain is held constant for a given period of time. Okay, so it's time dependent. So if we go back, so a decrease in stress when the strain is held constant for a period of given time. Meaning that if we go back to here, okay, the strain, so if we hold the strain, right? So go back here. So decrease in stress when the strain is held. So when we stretch, we change the length of the muscle, correct? Okay, the longer that we hold that, we decrease the amount of stress or force that is placed, okay, at that joint. And you can see that over time. Then we have something that's called creep. Okay, so this is stress relaxation, what we see with stretching. Then we have creep, which is an increase in strain, okay, when the stress is held for a constant period of time. So creep is an increased tensity towards more strain and plastic deformation with no change in stress. which makes sense because as we are stretching, okay, we're not increasing the stress, right? But we typically see the strain, right? We see an increase in the change of length or elongation for a given period of time. Then we have strain rate dependency. So when mechanical properties are dependent upon the rate change of strain. So typically, or to think of it, so the rate of strain is how quickly the strain is changing over time. So in general, strength, stiffness, and toughness of the viscoelastic material increases with increasing strain rate. So this helps our tissues actually protect themselves. Now looking at the general mechanics of an injury, we're going to move pretty quick. We're going to look at mechanics of an injury, go over bone real fast, some tendon and ligament stuff, and then call it. So we have how can we stay free from injury? So we have something called material failure or breaking apart of material. So maximum stress exceeds the ultimate stress, or strain exceeds the maximum amount of strain. Okay, again, that change length. So typically when we see energy entering more quickly than it is leaving, it must go somewhere, which results in some type of crack and or possible break or tear. So what we want to look at is we want to stay within this margin of safety right here. So we have a failure tolerance, which is the stress level above which failure can occur. We have the actual stress, how much stress is actually placed on the body, and then this margin of safety. So if we think of it, dropping something on your foot, that stress is going to exceed the material. Another example, if a load is applied at the right frequency, biological responses will occur in the tissue that will improve its ability to handle stress. That is, increase its failure tolerance. However, if the frequency of loading is too high, we are overtraining, the tissue will fatigue and the failure tolerance will begin to decline, as well as the margin of safety, here being our failure tolerance right in here. So our types of injury, we have acute, chronic. Acute happens immediately, chronic over time. Okay, how we can decrease injury risk. Okay, specifically if we're looking at exercise, so we can decrease the applied stress by looking at by decreasing the amount of force or increasing the amount of area. If we increase our cross-sectional area of the muscle, okay, then we can obviously decrease the applied stress, right? As we get stronger, as we get bigger, stronger, muscle is bigger, okay, it helps to distribute that force, okay, which decreases our injury risk, which is why resistance training is part of every athlete's program. So here's some questions that we have for us. Let's look at bone real quick. I'm going to let you guys go through all of this stuff. You guys should understand the structure of bones. You guys are in A&P currently or have taken it. So I want to focus real quick, though, the difference again between mechanopathology and pathomechanics. Mechanopathology, the mechanics that result in an injury. Pathomechanics, the mechanics that are the result of an injury. So fracture, breaking a bone, okay, acute, instantaneous, okay, stress fracture is going to occur over time. We have osteopenia, which is low bone mineral density. Osteoporosis is severe decrease, so you actually get have an exceedingly low bone mineral density. And then usually we see age and disuse with an inverse relationship in terms of bone health. Basically, we became sedentary as we aged. So we have different types of cartilage. You guys should be familiar with these types of cartilage as well. Okay, they help to distribute the load transmitted across the joint. Okay, allows for allows for relative movement of two opposing joint surfaces with minimal wear and tear and decreases friction. Think of your meniscus, right? They lubricate the joint, help with load under tension. You guys can look there. Cartilage. What do I want to get to before we run out of time? This right here is a prime example showing that moderate repetitive loading brings desired changes and increases the thickness, okay, and proteoglycan content and decreased removal. Negative wear seen is with immobilization or high intensity loading. So our last one, ligaments. Here's the function of the ligaments. I'm going to let you guys read those. Okay, pretty much resist tensile loads. Okay, there's the definition of a sprain. You guys can read that, and that's the last slide.